Jnanam Paramam Dheyam. Knowledge is supreme.
So, we will continue sometime our study of DVRs, discrete valuation rings. I want to give a characterization of normal domains in terms of discrete valuation rings. So, the theorem we would prove first is let A be an Noetherian integral domain. Then the following are equivalent. One, A is a normal domain. A is normal, already domain. 2, for every height 1 prime, for every P prime ideal of height 1, the localization of A at P is a DVR, and every prime ideal Q which is associated to principal ideal to a non-zero principal ideal as height of Q is 1. That is second condition. Third one, same for every P prime ideal of height 1, A localized at P is a DVR, and if I take the intersection over all height 1 primes, A localization at P, this intersection is happening in the quotient field of A, because A is a domain, all localizations are subrings of the quotient field. So, this intersection is here. So, this is A. So, then these three conditions are equivalent. So, normality you can characterize by discrete valuation rings at height 1 primes. Okay, so let us prove this. So, proof. I am going to prove 1 implies 2 implies 3 implies 1. So, first 1 implies 2, 1 we are assuming normal. The first part is clear because if P is of height 1, then this is also the dimension of the localization, and it's one dimensional local ring, and because A is normal, localization is also normal. So, it is one dimensional Noetherian integrally closed ring. So, therefore, it is a DVR. So, A normal by 1. So, that implies AP normal, and hence by earlier theorem that AP is a DVR. Second condition, we have to prove that every prime ideal Q which is associated to a non-zero principal ideal should be height 1. Okay, so let us take a prime ideal Q. Let Q be a prime ideal, and suppose Q is associated to A mod AA, where A is a non-zero element. That is the meaning that Q is associated to a non-zero principal ideal, and therefore, if I localize at Q, AQ, this will be associated to A localized at Q, A localized at QA. Further localization associated remains associated. Therefore, look at this ring A localized at Q. This is a local ring where maximal ideal is associated to a non-zero principal ideal, and that was one of the criterion when we characterize DVRs. If you have a local ring where the maximal ideal is associated to a principal ideal, it's a DVR, it's height 1. So, this is DVR, and therefore, height Q is 1. So, that proves 1 implies 2, or 2 implies 3. We have given that at height 1 primes the localizations are DVR. So, the same condition is given in 3 also. So, we only have to prove that the intersection, so only to show A is equal to the intersection of APs, where P is running over height P equal to 1. This is what we have to prove. And in this also, this inclusion is clear because A to AP is always injective. This is injective, and it's everything happening in the quotient field. So, therefore, we only have to prove the other way inclusion. So, for that let's take X in the RHS, and I want to prove that X is in A. Okay, so X is in the quotient field because this intersection is happening in the quotient field. So, therefore, this X belong to, that is X belong to the quotient field of A. So, we can write X as a fraction A over B, where A, B are elements in A and B is non-zero. Alright, now I will use the primary decomposition for the principal ideal B. So, look at the ideal B, ideal generated by B, and look at its primary decomposition. So, this is equal to Q1 intersection QR be the primary decomposition. Of the principal ideal B, and we take the reduced primary decomposition, and the corresponding associated primes, let us denote them by P1 to PR, associated primes. Okay, but in 2 we are assuming that if we have a prime ideal Q which is associated to a non-zero principal ideal, it has to have height 1. So, all these P's will have height 1, that is it's given in by assumption into all height Pi are 1 for I equal to 1 to R, because Pi's are associated to the principal ideal. So, when I localize B, localize at Pi, only Qi will survive. Because there can't be any inclusion relation between them. So, therefore, only Pi will survive. This is true for every I. But this means A by B, look at A by B, this was our X, and this belong to the all intersections running over height 1 primes. So, in particular this one belongs to A localized at Pi for all I. So, this simply means that the ideal the element A belongs to the ideal B generated by B in A localized at Pi, but this is Qi A localized at Pi, and this is true for all I. But then but on the other hand, this A also belongs to the ring A. So, therefore, this A belongs to A intersection Qi A localized at Pi. This is true for all I, but this is same as this is a primary component, we have localized it and intersect back. So, this is you get back Qi. This is true for every I. But then A belong to the intersection. So, that is A belong to the intersection of Q1 intersection Qr, which was the primary decomposition of the principal ideal B. So, A belongs to the principal ideal B. So, that will imply A by B, which was X, this will belong to A, because this A is a multiple of B. When I write A multiple of B, B gets cancelled and you get in A. So, that proves 2 implies 3. Now, let us prove 3 implies 1. So, 3 is, we have given 3, that is all height 1 primes, APs are DVRs, and intersection of localization at P, where intersection is running over height 1 primes, should be the ring A, and from here we want to prove the ring is normal. So, that means we want to show that A is an integrally closed domain. We have already given A is an Noetherian integral domain. So, enough to prove that A is integrally closed. A is integrally closed. That means we have to prove that if you have an element in the quotient field, alpha belongs to the quotient field of A, and if alpha is integral over A, then it should be in A. Okay, so alpha is integral over A. Suppose that alpha is integral over A, then remember we want to prove. So, this is what we want to prove, alpha belongs to A. Well, if alpha is integral over A, then also it will be integral over A localized at P for every P actually, because A localized at P is bigger ring than A. In particular, it will belong to and what is given in part of the 3, if I take height 1 primes, then it is a DVR. So, therefore, alpha belongs to A localized at P for all P with height of P equal to 1, because they are DVRs and DVRs are integrally closed. But then alpha will belong to alpha will belong to the intersection of all APs where this intersection is running over height p equal to 1. But by the second assumption in 3, this intersection is given to be A. So, this is by assumption in 3. So, that proves that alpha belongs to A, therefore, A is integrally closed, that is A is normal. Okay, so, I will mention one more theorem here which I will not prove. I think you might have seen earlier that this theorem, let A be a integral domain then A is normal if and only if a polynomial ring in finitely many variables x1 to xn is also is normal. This proof, I think maybe if I remember correctly, I have written in the supplements in exercise sheet 1. Okay. So, that now I want to prepare for Dedekind domains. So, Dedekind domain definition I give, but I want to give a characterization of Dedekind domains. So, first, so we want to start with Dedekind domains. So, to give the motivation, Dedekind these are named after Dedekind, and Dedekind wanted to abstractize the properties which are in the ring of integers. So, ring of integers we know elementary theorem of elementary fundamental theorem on elementary number theory says that every integer, non-zero integer, is a product of prime numbers, and this product is essentially unique. That means up to an order of the primes and up to the associates, but associates in these rings are just plus minus 1, the units are not too big. So, now if I want to generalize this in a integral domain first, let us say integral domain, but now several difficulties will occur, namely the unit group may be too big. So, we can't say, okay, that is one difficulty. Another one is definition of prime. So, prime numbers here will correspond to the prime ideals. The definitions, right. So, these are now denoted by the Gothic letters P, and now the usual integers are replaced by the ideals. See, the divisibility is replaced by the containment. So, then one would like to know, or one would like to characterize all integral domains which have the property that every ideal in that is a product of prime ideals, and essentially in a unique way. So, this is the theorem we want to prove. So, those rings are called Dedekind domains. So, this is one of the characterization. And then definitions, then now people make always abstract definitions. So, the definition was, we will take these as the definition, and what I said, that will be the theorem. So, the definition says a Noetherian integral domain is called a Dedekind domain if it is integrally closed dimension of dimension it's a less equal to 1. So, obviously dimension will be 1 only because it is a domain. So, the only way that it is dimension 0 it is a field. So, this allows to say that the fields are Dedekind domains. Okay, so, we have example that fields are Dedekind domain. Also, PIDs are Dedekind domain. So, let us see few examples. So, few examples. One, any PID is a Dedekind domain. I will write DD or any DVR, in particular DVR implies it is a Dedekind domain. So, we have many examples here. So, polynomial ring over a field, yes, polynomial ring in one variable over a field, power series ring in one variable over a field. These are, this is a typically DVR, this is typically a PID. Ring of integers is also Dedekind. Okay. More than that, now another important aspect of the Dedekind domains was the following examples which do come from number theory. So, take a number field, K is a number field. Number field simply means it is a finite extension of Q. Finite field extension of Q is called a number field. And we have here the ring of integers, Q is a quotient field of Z, and now we take the integral closure of Z in K. So, that is some people denote it by OK or AK. So, this is the integral closure of Z in K. Now, question is whether is it a Dedekind domain. So, let us see what are the obvious facts. Obvious facts as it is a domain, dimension is 1 because this extension is integral and Z is dimension 1. So, dimension of AK is 1, also AK is integrally closed. So, the main difficulty is to prove it is Noetherian, and that is because of this is one of the motivation was for the Noether. Noether was the first who realized that it is important to study these examples, and so it is Noetherian. In fact, this more general or some remarks concerning this I have written in the exercise 3 latest I have added this. So, in fact, it will be a free module over Z of finite rank. So, in fact, AK is a free Z module of finite rank. This is also, this was proved by Stimke. this is not so difficult proof. I will add it in that what is equal to rank? Yes, rank will be equal to the degree of the field extension. Finite field of finite rank equal to K over Q. Okay, so all these are Dedekind domains. But now another question, another very important question from number theory and many other important questions. When is it a UFD? So this is a Dedekind domain, so it's a locally a PID. But when is it a, so when is AK UFD? This is still, this question still doesn't have a good satisfactory answer till today, even when the number field is of dimension 2, even quadratic extensions. For imaginary quadratic field extensions, there is a good answer, so that's by Gauss, and Gauss have guessed it, but it was proved later in 60s by Stark and others. The proof is not completely algebraic, it involves a lot of analytic number theory. And for the positive, I mean the real quadratic fields, it is still wide open even for degree 2 extensions. So there is a lot of scope to do research.